You ever get that feeling that your code base is a house of cards? Where adding just one simple feature means you have to create a whole bunch of new classes? If you've ever stared at a tangled mess of a class hierarchy and just sighed, well, this explainer is for you. We're going to talk about a design pattern that solves this exact problem, and it does it beautifully.
So here's what we're going to cover. First, we'll dive into what I'm calling the class explosion problem. Then we'll see how to solve it by building a bridge. We'll break down the anatomy of the pattern, see it in action with some real-world examples, and finally, we'll talk about when you should add this powerful tool to your own architectural toolkit. Okay, so we've all been there, right? You're building something new, and your first instinct is to use inheritance. I mean, it's a cornerstone of object-oriented programming. But pretty soon, you start to feel like you've painted yourself into a corner. Let's start with a super simple example. Say we have a base shape class, and we create circle and square subclasses. Easy enough. Now, we want to add colors. Let's go with red and blue. The most direct approach? Well, you create red circle, red square, and so on. 2 shapes, 2 colors. That gives us 4 classes. Seems manageable, right? For now. But you know how it goes. The product manager comes back with a small change request. They want to add a triangle shape and the color green. Sounds simple, but this is exactly where our inheritance model starts to show some serious cracks. And boom! Just like that, we've gone from 4 classes to 9. And look at the trend here. If we add just one more shape, we have to add 3 new classes. If we add one more color, we have to add another 3 new classes. This isn't growing linearly, it's a geometric expansion. And folks, that is what we call the class explosion. The real problem here is that we have 2 completely independent ideas or dimensions that are changing, the shape's form and its color. And we're trying to cram both of them into a single rigid class hierarchy. That just doesn't scale. So, what's the fix? How do we escape this mess? Well, instead of building this one big, teetering tower of classes, we're going to do something smarter. We're going to build a bridge that connects 2 completely separate, much more flexible structures. And that solution, my friends, is called the bridge pattern. The whole point of it is to decouple an abstraction from its implementation. What does that mean? It means we can change our shapes and our colors completely independently of one another without this crazy explosion of classes. Now, to get this, you have to make a pretty fundamental mental shift. We're moving away from that rigid is-a relationship we get with inheritance. A red circle is a very specific kind of shape. Instead, we're moving to a much more flexible has-a relationship, which is called composition. So a circle has a color. See the difference? And this all circles back to one of the most powerful principles in all of software design. You'll hear it all the time. When you favor composition, you build systems that are just way more flexible, way more scalable. And that principle, that is the absolute heart of the bridge pattern. Okay, so the official names for the parts of this pattern, abstraction, implementer, they can sound a little academic, a little textbooky, but trust me, the ideas behind them are actually really simple. Let's break them down. All right, first up is the abstraction. Just think of this as the thing the client interacts with. It's the high-level control. A classic example is a generic remote control. It's got the buttons, right? Power, volume up, volume down. But here's the key. The remote itself doesn't know how to turn on a TV. It just knows it has a job to do, and it needs to delegate that job to something else. And what's cool is you can then extend this abstraction side of the bridge all on its own. For instance, you could have an advanced remote control that adds a mute button. Notice this whole remote control hierarchy has absolutely nothing to do with the devices it's actually controlling. It's totally separate. Now let's walk over to the other side of the bridge. This is where we find the implementer. This is basically an interface that defines the low-level, primitive operations that the worker classes can perform. So for our remote example, this would be a generic device interface with methods like enable, disable, and set volume. And finally, you have the concrete implementers. These are the real workhorses. These are the classes that actually do the job. So a TV class and a radio class would both implement that device interface, but each one would have its own specific logic for how to actually turn on or change the volume. Okay, theory is great and all, but where the rubber really meets the road is in the real world. Let's see how this structure gives us some serious power and flexibility in actual applications. So let's walk through that remote example step by step.
First, the client code connects a TV object to a remote control object. Then, when the user hits the power button, the client just calls remote.togglePower. The remote, our abstraction, doesn't know anything about TVs. It just delegates that call to whatever device it's holding onto. And finally, the TV object, our implementation, gets the call and does the actual work. All right, here's another fantastic example you've probably encountered: a payment processing system. Think about it. You've got two things that can change independently. First, there's the payment method that the customer sees, like paying with a credit card or using net banking. And second, there's the back-end payment gateway that actually processes the transaction, like Citibank or IDBI. See what's happening here? By building a bridge, we can treat the payment method as our abstraction and the payment gateway as our implementation. This means we can mix and match any payment method with any gateway we have, all at runtime. We don't have to create a ridiculous card payment via Citibank class. The flexibility we gain is just immense. So the bridge pattern is obviously super powerful. But like any tool, you don't use a sledgehammer to hang a picture frame, right? So the big question is, when should you actually pull this out of your toolkit? Think of this as your go-to checklist. You should reach for the bridge pattern when you're looking at a giant monolithic class and thinking, this thing needs to be split up. Use it when you spot those independent or orthogonal dimensions of change, like our shapes and colors. Use it when you want to avoid locking an abstraction to a specific implementation forever. And definitely use it when you need the flexibility to switch out those implementations at runtime. So let's break it down. Pros and cons. The pros are huge. You can build platform-independent systems, and you're following some really solid design principles, like the open/close principle and the single responsibility principle. Now, what about the cons? Well, the main thing to watch out for is over-engineering. For really simple cases where things probably aren't going to change, it can add a layer of complexity that you just don't need. Okay, this is a big one. People get the bridge and adapter patterns mixed up all the time, and it's easy to see why. But the difference really comes down to timing and intent. You use the bridge pattern up front, during the initial design, to build in flexibility from the start. You use the adapter pattern after the fact to make two existing classes that weren't designed to work together, well, work together. So bridge is about design, while adapter is about repair. And that's a wrap. So as you head back to your own work, I want you to think about this. What independent dimensions exist in the systems you're building right now? Could building a bridge today prevent a class explosion for you tomorrow? Thinking about this pattern, it can honestly be the difference between a brittle, high-maintenance codebase and a truly scalable, elegant architecture.